Next up, Sven Böcker, Johan Westlund, and Johan Nygren for KTH Formula Student. Welcome.
Hello? Do we have the clicker thing? And how does it work? I assume you click it. Thanks everyone for coming. Thanks to Suna and everyone else for organizing this event and for inviting us. We're very happy to be here, and we're glad that you'd rather listen to us than watch the football games. So the topic of this presentation yeah. The topic of this presentation is how to control an electric race car. And just a brief introduction of me. My name is Sven Böcker. I am the corporate relations and marketing lead of KTH Formula Student, and these are my colleagues. You can hold the mic.
Yeah. Johan Nygren, and I am the lead for the low voltage electronics in the car.
And I'm Johan Westlund, and I'm the lead for the powertrain electronic system overall in the car.
So, starting off, what is Formula Student? Well, it is the biggest engineering competition in the world for students, and it is sort of a testing ground for student engineers who will become the best in the world afterwards, or at least according to us. Let's see, we can start with the competition. It is an international competition. There are more than 400 teams in the world. It races on 4 continents, as well as 5 in Europe. And these take place, if you guys step aside, we have in Great Britain, we have in Spain, we have in Hungary, Italy, and Germany. The whole competition, this Formula Student, which is also called Formula SAE for Society of Automotive Engineers, was created during the late 70s, beginning of the 80s by people from Formula One and automotive industry in order to prepare students in engineering for real-world projects in engineering, which was something they thought was lacking. Because engineering is not just about creating something, it is about motivating why you did it, and it's not really easy. We have a competition that is composed of dynamic events and static events. So the idea is to design and build a fully functional race car. This is done by teams of students at universities, and the dynamic events are dynamic, meaning that you test the car, you drive it, and then you have the static events that I will move on to now. We have cost and manufacturing, we have business presentation, and we have the design presentation. And basically what this means is, how well do you know the car you've built? How well can you motivate the design choices? And how much would it cost if you were to actually manufacture it without these sponsors you've had? And if you had the technology you use for industrial grade manufacturing, how much would it cost? And then you have the business presentation, where it's basically, if you've seen Dragons, then you have to pitch the car, try to get an investor to invest their money in it. Then we have the dynamic events, and first off is the acceleration, where you go from standstill, then you drive 75 meters as fast as possible. And mind you, these cars aren't slow. You might have heard of the energy efficient cars driving far on little consumption. These are more 0 to 100 kilometers an hour in 3-4 seconds. So yeah, acceleration, one part. Then we have the skid pad, which is basically testing the car's handling ability or cornering. So you drive in an 8 as fast as possible without hitting the cones. Then we have the autocross, which is 1 lap around 1 kilometer on a track composed of cones, and it's a very narrow track, and it's not very, there aren't any long straights, so you don't really need the top speed. It's more to have a generally good car. And then we have the toughest of them all, which is the endurance. And here you test all aspects of the car, because the car has to be able to drive 22 kilometers in a long race. And considering that these are race cars, they aren't supposed to drive for 2 hours, for example, because that would require too much fuel or too big of batteries to actually make it a race car. But then we also have the efficiency from the engine, be it fuel, like in an internal combustion engine, or electricity. And it should be added that both electric and internal combustion engine cars compete together. This means that the electric cars have to be very limited in order to outperform the others too much. KTH Formula Student then. We are the first electric Formula Student team in Sweden. There are a few more. There are Chalmers in Göteborg. They're also electric. The rest are internal combustion engine. We started in 2003. 7 combustion engine cars, and then we moved on to electric. It is the biggest student engineering project at KTH, and we have around 30-40 members each year from all different programs at KTH, as well as from many different countries. Here you can see us, some of us members from last year, when we were at the competition at Silverstone, and we actually won the Energy Efficiency Award. So I think now it's time for Johan Nygren.
Great. So now you basically understand what we do and why we do it, or rather, why we do what we do. Well, we want to compete. This is a 3D render of our new car, which we have been building this year. To clear out one thing, we build one car every year. So basically we don't have 2 years to prepare, we have 1 year to design, build and test the car and then go to the competition. At least that is how we normally do it. You can choose to develop a car in a lot of years and then you just run it once. But from the start you have been, if you have run a car on a competition, you have 1 year from that date to actually use that car, and then you need to make a new one to compete. So for this year, we have moved up and we have designed a system where the low voltage runs on 24 volts, a high voltage battery to run the motors, that is 567 volts, and a peak amp of 100 amps. And continuous, it's not just, sorry I said peak, but it's continuous driving for 100 amps, which is important because we need power in the long run, not just short amounts of bursts for the longer drives. And also when we want to regen from the motors, if we pull out energy and the driver wants to slow down, we don't want to waste that energy. We don't want to turn it into heat in the brakes. We actually want to reinvest it into the battery so we can use it again. And to be able to do that, the battery needs to be huge. It needs to be able to handle that amount of energy being put back into it. So for motors, we use 2 motors, 1 for each back wheel. The reason for this is we don't need any mechanical shifting between the 2 wheels. We can electrically control each wheel and therefore make it very, very efficient in specific cornerings. And we have chosen MREX for this. They're pretty big, but they are a standard component. Unitech is our developer for inverters. We do not make our own. We do make our own housings, and we control them ourselves. But manufacturing an inverter in 1 year is a huge task. So therefore, we went to buying off-the-shelf components because it's a lot easier. I should mention, the previous car weighed around 300 kilograms. The new one is supposed to be 220, which is a huge weight loss. So we basically put the car on Biggest Loser. Yeah, probably we did. So, to the electric system, because I'm the low voltage lead for this car. So how do we control it? Well, it's an electric car. We can't really use mechanical things to control electricity. We need electricity. So we use sensors, a lot of them. And every red line you can see is actually a sensor wire, basically. This is a crude representation of the car, where this is supposed to be kind of the wheel, because it's a wheel speed sensor, and then you can see the little damper sensor that can detect the actuator on the damp. You also have a Hall sensor to see the torque, and some brake pressuring sensors. The brakes, we do use a mechanical brake system, because using an electrical brake system in a car built in 1 year without testing, that's kind of stupid. It really is stupid. We do have a main control board where you can see all the blue lines, kind of, which is our brain, you can say. We have a lot of our own developed PCBs, and I will start out with a little bit about the sensors, and then we'll move along to how we actually use these. First off, throttle. It's a Hall effect sensor. It's no mechanical components touching each other, so it will not wear out. This is important. You do not want your throttle to wear out, so it's stuck on full gas when you want to take a corner. Brake pressure sensors? Well, it's a sensor that just detect the pressure. They don't really do much in terms of controlling the car, but they do limit the effect that you are able to put out. The wheel speed sensors, also Hall effect sensors for the same reason as the throttle. You don't want something that can wear out over time. Steering, linear. This is the first year for us. We haven't used the linear displacement sensors for this. This is the first time, and the reason is we want higher accuracy. We have the IMU, a standard accelerometer, gyroscope, compass, and GPS. The BMS is battery management system, and you have voltage, temperature, and monitoring. And then you have the resolver, which is on the motor to detect the polarity of the magnets inside of the motor. All right, let's start with throttle and brake sensors. Here we have sponsors from Panagile and also ADC Nygren, which makes where Panagile makes our linear sensors, and we have two because we do need it to be robust. If one sensor breaks, the other one will detect that and shut down the car. This is a rule. We do have a lot of rules in this competition. It is an engineering competition based on design, so having a good design for them to judge, they need rules to judge by. And this is a security thing too. If one sensor deviates too much from the other, the car should also shut down. Because if the car says full gas, but the driver actually only says it, well, I want 10%, that's not going to end up too good. So, wheel speed, damper, and steering. This is not a direct input from the driver. This is actually a response from the car. All right, I'm in this state right now. The driver wants this speed or this brake. And our electronic system is supposed to deliver the driver's what the driver wants. And by measuring the real world, we can actually make this more efficient than if we would have just had direct drive. Yeah, and then I will leave to Johan Westlund to talk about the rest of the car.
So I will take the last sensor, talk about the battery management system, and that is used to monitor all the 270 battery cells in the cars, so we see that they are in the voltage and temperature limits of what the manufacturer recommends, and also to balance the cells so they are good, like have the same charge for in all of them, by using power resistors to dissipate the overcharge from the overcharged cells. And then you can see how we get the battery electric energy in the battery to the inverter, and then out to the two motors one for each back wheel. And to control this, because we don't have mechanical differential, we got a main controller sponsored by Fenco up in Danderyd that gave us this micro auto box that's a power PC able to run compiled Simulink code really good, so you can use Simulink and really fasten up the design using model-based design that we have used for developing the controllers for the car. So our vehicle dynamics group have made a model of the car, put a controller on that model, run it several times, and then we just quickly put it on this micro auto box to test it in the real world without doing any low-level C coding and stuff. And then we'll explain what the vehicle dynamics group did was basically to develop this controller for the different function we want. So from the sensors, we want to limit the power because of both the rules and also to keep the battery in a good condition. And then traction control is what you can see on that picture. Testing, it's a bit sloppy. And torque vectoring is for keeping for the electrical differential. And then they put this on a simulator that we have in the garage, and then we can just in a few minutes put it on the car and test it. So now I will try to show a video of how it looks without the controlling, without all the sensors, and then after. So this one is without any controllers, and you can see it slips all the times. But so you can play it again. That one shows, you can see it's like, and that one we have, it's our first prototype, so it was a bit crude, but it shows that we get the sensor and things and just don't put it out directly, but do some calculation in the controller to get some optimum friction of the wheels and tires, so we can get a good start in the acceleration. So this is just a brief presentation of the car, but we can get in more details when we go down to the car later. Thank you.
Just a second. You might have seen the car outside before. We're gonna bring it back. We just stored it away for a few minutes, but we're gonna bring it out during the break. So you're more than welcome to come and look at it. And if you're brave enough, you can definitely sit in it. Yeah, first question. Yes, we have what we use for dampers. Yes, we have Öhlins. Öhlins actually are very popular in this Formula Student community, and we were lucky to get one of their, shall we say, specialized dampers for Formula Student teams. You don't want to know. It's probably more than you can afford. It's a bit more than we can afford, actually, which is why we have a lot of sponsors. We would not be able to do this without them. But that's part of the cost event as well, that you have to see how much would it cost if you would account for manufacturing both time and material-wise. The last one was made in glass fiber. This one will be made in ABS plastic.
Tubular frame.
It's a steel tubular frame this year, or it's been quite a while. We've done monocoque before, but working in carbon fiber is very difficult.
Yes, what kind of communication is used in the car? It's CAN bus everywhere, basically. We have two buses, one from the main controller to the inverters, So we have that isolated from the rest of the system. And then all of the sensor boards that collect data from the sensors send communication over the CAN bus to the main controller as well, over one bus. The question is what course this is, and the answer is none for the course, but the time is too much. The truth is, this is a voluntary project. We as students need to volunteer for the project, and we do have to kind of lay at least, we say, 20 hours a week.
Probably more.
Yeah, we say we want people to spend 20 hours a week, but that's not true at all. I wish it was 20 hours a week. Then I would have, well, a life. But so yeah, the answer to the question is with no course, this is voluntarily, and it's over 20 hours a week.